In order to understand this whole order versus chaos thing, we're going to look back at our temperature model. Because remember, when we have different temperatures, different energy levels, we're going to move from the high energy to the low energy. So what I've drawn up here is two chambers of gas. We're just pretending this is just air. This is just air. Nothing special, plain old air. We've got on one side really hot air. Let's say it's about 100 degrees Celsius. On the other side, let's say it's about 0 degrees Celsius. It's colder, this is hotter. I've got the two rooms divided by this impenetrable barrier. The air can't be exchanged. As long as this barrier is here, if the hot air tries to go through, it'll bounce off this and stay in its room. If the cold air hits it, it'll stay. But what happens when I remove the barrier? Right when I remove this, if I've got a bunch of hot air molecules here, they're going to keep bouncing around just like they were before, except now when they get over here, they can freely move to the other side. The same thing happens with the blue arrows, but they're moving much slower. What do you think is going to happen? We can see right off the bat, I've got some molecules that are already pointed in this direction. As soon as that barrier is out, they're going to bounce in. So let's draw those guys. These three right here, they're going in. So, right off the bat, we've got three of our hot air molecules moving to the other side. What's going to happen to the cold air molecules? Well, they're also going to move. I mean, I've got this guy heading right for that area. Got this guy heading in. He's going to get there, but he's going to be a lot slower. So by the time these hot air molecules get in here, our cold air molecules have barely moved. So the reality is all of it's moving. The hot air is going to move in this direction steadily. It's all going to try and even out eventually. The cold air is also going to try and move over here. In fact, what's going to happen is the hot air is going to move in so much quicker, but that's going to make all this extra room. It's going to get really crowded in this room, and stuff is going to be more likely to go to this side. Just like when we've got a jar of water that we tip on its side, it's going to spill out because there's less water over here. There's more room for the water to move. If there's more room for the water to move, the water's going to move. The same thing's going to happen with these molecules. If there's room, if there's a place for them to go, they're going to go there. Because now suddenly, even with just this setup, these guys have left this room. There is vacancy in this room, and this one's looking awfully crowded. So over time, all of these molecules are going to move around. And eventually, we're going to have two rooms that have a really even mixture of some molecules that have a lot of energy and some molecules that don't have a lot of energy. So if we had the same amount of gas in both rooms, and we said that this one was 100 degrees, and this one was 0 degrees, well, at the end of it, after everything gets mixed around, they're probably going to average out between the two about 50 degrees. Because we're mixing all of these really fast-moving particles with all these really slow-moving particles. Now, which one was more ordered? Which one was more chaotic? Well, obviously, the first one had a lot more order. We had a clear sorting between the fast molecules and the slow molecules. And over time, once we allowed those two things to intermingle, we had a really even mix. It's a lot more chaotic. Let's extrapolate this example. So now, if the system earlier was ordered, this one is super ordered. It's very well organized. I've got all of my really fast particles here, all of my medium particles here, all of my slow particles here. But if they've got these gaps, over time, all of these are going to mix because they're all in motion. Now, once it's mixed up, how able would it be to get back to this condition? So think about that. I'm going to mix these all up now. I'm going to get some reds moving along. I'm going to get some blues moving back and forth. Purple's going to go every which way. And I want you to think about, once it's mixed up, how likely is it to get back to this really ordered situation? So now all three of our rooms are really mixed up. How likely is it that these are going to go back to our starting conditions? That all of my purples will migrate and find their way into this middle place. All of my blues will find their way over to the right side. All my reds will find their way over to the left side, and everything will be nice and separated and orderly. It's not likely at all. It's basically never going to happen. How could it? As soon as a red goes this way, it's probably going to bump into a blue and send itself back in here. So we can have this really ordered condition, but it's really easily going to turn into this more chaotic version of it. So let's look at a real example of that. Okay, so at my workbench here, let's create a really ordered environment. Let's just use these nice dry erase markers. They all have different colors. I'm going to order them according to their colors, according to their types, all kinds of things. Now look at all that time and effort that cost me. It took a lot of energy for me. I had to expend a bunch of energy to make this nice, ordered system. I had to spend a bunch of effort and time. Now, what would it take to, without me putting in any effort, cause all of this to fall down and break apart? I mean, imagine, I live on Main Street. All it would take is a big enough truck rumbling by in the middle of the night, waking me up, and crashing my nice orderly palace to pieces. An earthquake could pass by, a strong wind could shake the building, a tornado could happen. I could leave my windows open and a gust could pass through, and it could cause this whole thing to just fall easily. And once it's fallen, this is a lot more disordered. There's nothing orderly about this. And if enough time passed, these would fall, these would break apart, these things would mix together. Enough time and circumstance passes, and these things can very easily, without any intentional effort on any person's part, they could fall apart. And even now, I'm putting them in a nice orderly pile. If this actually occurred, some of them would fall off the edge of the table. They'd go all over the place. It takes no effort to make a mess. It takes absolutely none. It is a natural occurrence of the laws of physics. It's a lot easier for these things to fall to pieces. Now, what are the chances? What would have to happen besides me coming in and putting that all back together for these markers to get back up on the table and take that nice orderly position again? It's impossible. It's not going to happen. So when we talk about order versus chaos, it's very close to how energy moves around. Because remember, this was just what, 10 markers? I made a nice orderly system and it fell apart in no time. Imagine a mole of water. Remember, it's not much. I have in my water jug right now, I have about a mole of water in here. It's really not much. If I fill this whole thing up, I'd have about five moles of water. How many particles was that again? In one mole? That was 6.022, and then put another 22 zeros after that. I'm sorry, another 19 zeros after that. Move this decimal place 22 places all the way down. That is a massive number. Now try and keep all those particles organized. What do you think is going to happen to those? When some have more energy, when some want to move around, of course they're going to get more disordered. They're going to get more disorganized. Is that a natural process? Is there any way for these things to become less chaotic, to become more organized naturally? Tomorrow we're going to define the law that governs this whole idea. It's incredibly useful, and it explains how everything from markers falling and not standing back up to things like refrigeration, perspiration, and why heat flows from a candle outward.